Hi, my name is Jenna Henderson. I'm from Georgia State University, and on behalf of my co-authors Diego Ferreira and Jerry Wu, I'm going to be presenting on the correlation between forward and backward treadmill walking in typically developing school-age children. So backward walking has been described in the literature as being a time reversal of forward walking, suggesting that the two gait patterns may be driven by a similar neural mechanism. High correlations in joint kinematics between forward and time reverse backward walking have been reported in both adults and school-age children. However, most literature examining these correlations in adults and children has focused on overground walking rather than walking on a treadmill. Backward treadmill walking is often used in the clinic as a therapeutic modality to improve overground gait in people with a variety of disabilities. It's well established in the literature that there are significant differences between overground gait and treadmill gait in both adults and children, but despite this and the frequent use of backward treadmill walking clinically, responses to changes in walking direction on a treadmill are not well studied. Therefore, the purpose of this study is to investigate the correlations between forward and backward walking kinematics and kinetics in typically developing school-age children during treadmill walking at different speeds. We hypothesized that both lower body kinematic and kinetic variables would be highly correlated between forward walking and time reverse backward walking on a treadmill at all speeds. So to do this, we recruited 19 typically developing children between the ages of 6 and 12, and they each completed 6 bouts of treadmill walking for 2 minutes each. This included bouts going forward and backward at each of 3 speeds: a slow speed, which represented 75% of their typical overground pace, a normal speed, which represented 100% of their typical overground pace, and a fast speed, which represented 125% of their typical overground pace. We collected lower body kinematic and EMG data, and then correlations between forward walking and time reverse backward walking were calculated, including kinematics at the hip, knee, and ankle, and vertical ground reaction force. So for our results, the table here on the left shows the coefficient of determination between forward walking and time reverse backward walking at all 3 speeds. And then the graphs on the right here illustrate those findings in the normal speed condition. So as you can see here, the kinematics at the hip are very similar for forward and time reverse backward walking. A similar trend is seen at the knee, and this is supported by our R-squared values, which are quite high with really minimal variability at the hip and knee for all 3 speed conditions. Our vertical ground reaction force is also fairly correlated in the normal speed conditions, with the correlations decreasing at faster speeds, which is fairly similar to what is seen in the adult literature. At the ankle, however, some differences emerge. As you can see in this graph, our ankle kinematics are very dissimilar between the forward and time reverse backward walking conditions, and this is supported by our very low R-square values at all 3 speeds with very high variability, very high standard deviations. So what we found in general is that school-age children tend to adapt their ankle motion differently than adults during backward walking on a treadmill. We found that they adapted by limiting their ankle range of motion and by using their ankle plantar flexors less than what's been reported in the adult literature. This discrepancy is in line with the poor correlations we saw at the ankle between these 2 walking conditions, and we suggest, therefore, that proximal control at the hip and knee may be mature by this age, but that distal control at the ankle is still lacking. So perhaps the neural control for backward walking is still developing in school-age children, but this only becomes apparent when they're challenged to walk on a moving treadmill belt instead of overground. And this is in line with some previous literature that has found that some intersegmental kinematics during treadmill walking are continuing to mature up into middle adolescence. Some limitations of the study are a relatively small sample size with a larger age range, and this prohibited us from being able to determine if neural control at the ankle is actively maturing between the ages of 6 and 12. So further research examining exactly when this control matures in typically developing children, as well as research examining these correlations in children with disabilities, is still needed. You can see here at the bottom of the slide, I've got the contact information for both myself and for Jerry Wu. And so if you have any questions about this work or anything that you would like to suggest, please feel free to reach out and contact us. Thank you so much.